Hello, my name is Jenni Rytilä and I'm a doctoral student from Tampere University. In this presentation, I will be talking about how social ontology can be useful for philosophy of mathematics. I will do this by examining a certain view about the nature of mathematical reality called mathematical social constructivism, and in particular, Julian C. Cole's institutional account of the construction of mathematical reality. I'll analyze what merits social constructivism has and what challenges it faces. I'll focus on two major challenges, objectivity and applicability, and look at how Cole's theory deals with these. So let's start with what mathematical social constructivism is. It is a metaphysical theory about what mathematical reality is like. It tries to answer the question of what is the ontological nature of the subject matter of mathematics, which include things like numbers and sets. The subject matter of mathematics can be either objects or structures, but I will here leave this ambiguous and talk about entities, using it as an inclusive term. The core idea of social constructivism is that mathematical entities are social constructs that exist in virtue of social practices, in a similar way to more familiar social constructs like institutions, money, and the like. So according to this view, mathematical reality is a part of social reality. One motivation for holding such a view about mathematics comes from the practice of doing mathematics. Julian Cole describes an ontological puzzle that arises from two different aspects of mathematical practice. The first is that mathematicians routinely make ontological commitments to existing entities. There is also a clear sense of discovery in the experience of researching mathematics. Mathematical entities seem to have objective features that we can find out. The second aspect is that mathematicians freely and creatively postulate new mathematical entities in the course of solving problems. And as Cole notes, these are both legitimate practices that mathematicians have an authority to do. The puzzle is that traditional metaphysical interpretations for mathematics fail to explain both of these aspects. If we take ontological commitments seriously, this points us towards Platonism, according to which mathematical entities are abstract, non-spatio-temporal entities that exist independently. But the freedom to creatively postulate new entities is a problem for Platonism, because we have no guarantees that the entities we do postulate actually are those that exist independently. The practice of creative postulation agrees well with fictionalism and other nominalist ontologies that do not see mathematical entities as actually real. But they, in turn, invalidate the ontological commitments made in the practice of mathematics. And a third option, empiricism, according to which mathematics is about the features of the natural world, has trouble with both of these aspects. The natural world is not vast enough to substantiate all of the ontological commitments made in modern mathematics, and the features of the physical world significantly restrict the possibility of creative postulation. So how can we explain both of these aspects of mathematical practice? Cole argues that the solution to this puzzle is a metaphysical view that sees mathematical entities as real but dependent on practices. According to this view, mathematical entities belong to socially constructed reality. The point is to say that mathematical facets of reality are real in the same way that universities and money and other familiar parts of social reality are real. They are not independent of human activity, but they are genuine aspects of reality nevertheless. I'll now turn to Cole's more specific theory of the social construction of mathematical reality that he develops in his more recent research. Cole's account is institutional, and it is based on John Searle's theory of the construction of social reality. The central thesis of Cole's social constructivism is this: mathematical reality is the product of our collectively imposing function onto reality, where the functions in question are surrogacy functions with respect to logically possible systems of objects. Now, this thesis needs to be cleared up quite a bit. The first part is collectively imposing function onto reality. This refers to Searle's mechanism of how social reality is constructed. The idea is that a social entity like money exists because we collectively recognize that certain pieces of paper serve functions as of a means of exchange. And this applies to mathematical entities too. Things like numbers and sets are constructed by us to serve some functions. So Cole's theory states that mathematical entities are abstract institutional entities. And as institutional entities, they are products of systems of standing declarations, and their existence depends on collective recognition. The second part in this thesis is surrogacy functions. Surrogacy functions are a second kind of function besides status functions that Cole adds to Searle's theory. Surrogacy functions are imposed onto reality to help us, especially in representational activities, like inquiring and reasoning. These activities are made easier when the subject matter of our representations is treated as an object, even when it is not. These kinds of objects that are constructed to, as it were, stand in for other parts of reality, Cole calls surrogate objects. An example of a surrogate object that Cole gives is a border between nations. Nations carry deontic powers, and when we move from one nation to another, there is a transition in these deontic powers. And to help us represent this transition, we treat it as an object that has its own features. And by doing that, we construct a new collectively recognized social entity, a border, whose function is to represent the features of other entities than itself. In this case, the transition between neighboring nations. So the idea is that mathematical entities are surrogate objects that represent other parts of reality. And other surrogate objects include positions in organizations, possible worlds, and fictional characters. It should also be noted that surrogacy functions are so-called freestanding Y terms because they are not imposed onto some already existing object, and they do not coincide ontologically with any part of physical reality. The third part in the thesis says what mathematical entities specifically are surrogates for, and that is logically possible systems of objects. For example, natural numbers are surrogate objects which are constructed to represent logical possibilities about finite cardinalities. Any possible system of finite cardinalities forms an omega sequence, which means that it has a first member, second member, and so forth, but no last member. And natural numbers as institutional entities reflect that possible system. Now that we have a basic idea of Cole's theory, I'll move on to analyzing what merits and problems this theory and mathematical social constructivism in general have. Social constructivism about mathematics, like Cole's institutional theory, has some significant merits, both from the point of view of philosophy of mathematics and from the point of view of a more general ontological picture. First merit is that social constructivism agrees with mathematical practice. As a philosophy of mathematics, it is not revisionist. It does not try to tell mathematicians what they should do. As I see it, the aim in social constructivism is to make sense of what mathematicians are doing when they talk about mathematical objects. Also, as Cole argues, social constructivism as a metaphysical theory is compatible with both classical and constructive methodologies for mathematics. And as was already noted, social constructivism offers a solution to the ontological puzzle described earlier. It validates ontological commitments because mathematical entities genuinely exist as institutional entities, and it also validates creative postulation because mathematical entities are constructed. The second merit, which I think is the most significant reason to accept social constructivism, is that it provides an ontology for mathematics that fits into an overall scientific worldview. To paraphrase Searle, the aim is to answer this question. How can we reconcile a conception of the world as described by sciences with what we think we know about the subject matter of mathematics? Social constructivism does this by giving us a way to understand how mathematical objects can be real without postulating any Platonic realms. Any kind of independently existing mathematical world is a big problem for a worldview that is informed by sciences and, broadly speaking, naturalistic. But claiming that mathematical entities are real in the same way that legal borders and money are real is not in conflict with a naturalistic picture of the world, or at least not in any way to the same degree that a Platonist reality is. But despite these merits, social constructivism faces some challenges as a philosophy of mathematics. There are two major challenges facing social constructivism that relate to differences between mathematical entities and other entities of social reality. This is because mathematics has characteristic features that other aspects of social reality do not. The first one is objectivity. Mathematics is an epitome of objective knowledge, and compared to typical socially constructed entities, mathematical entities are quite non-contingent. The second feature is applicability. As is well known, applying mathematics in the natural sciences is very effective. And because this is the case, mathematical reality appears to be connected to the features of the physical world in a way that other facets of social reality are not. If we want to defend mathematical social constructivism as a viable philosophy of mathematics, the challenge is to explain these two features. In other words, we need to explain how and why mathematical entities are different from entities like fictional characters. Both belong to social reality and both are constructed by the same mechanism. And according to Cole's theory, both are surrogate objects. But fictional characters are very contingent and not at all useful in describing the physical world. So there are significant differences which require an explanation. So how does Cole's institutional theory meet these challenges? Cole's explanation for the objectivity of mathematics relies on Searle's distinction between ontological and epistemic objectivity. Ontological objectivity has to do with the existence of entities. Those entities that exist independently of experience are ontologically objective. Epistemic objectivity has to do with claims and propositional content. Objective claims are those whose truth or falsity can be ascertained independently of attitudes about them. But rather than epistemic objectivity, Cole talks about semantic objectivity, which has to do with whether a claim has a truth value independently. According to Cole's theory, mathematical entities are dependent on collective recognition, so they are not ontologically objective. But Cole argues that they are non-arbitrary. This is because in order to serve their surrogacy functions, they must have features in common with the parts of reality that they are surrogates for. However, mathematical claims are semantically objective. That is, they have truth values independently of the judgments of those who assess them. But this kind of objectivity is not yet enough, because claims about other socially constructed entities are semantically objective too, and mathematics should be objective in a much stronger sense than claims about, for example, genders. To explain this, Cole argues that the truth values of some semantically objective contents are constrained to be what they are by the features of ontologically objective facets of reality, and other contents are unconstrained. For example, true claims about the features of gender constructs are not constrained by anything ontologically objective and are therefore liable to change. This is in contrast with mathematical content, which in Cole's theory has semantic objectivity that is entirely constrained, because it directly represents features of ontologically objective facets of reality. For example, the statement 7 + 5 = 12 has the same truth value as when collections of 7 and 5 are combined, the result is a collection of 12. And this claim directly represents how concrete collections work, which is ontologically objective. So the explanation for the objective nature of mathematical knowledge is that mathematical constructs are constrained by other ontologically objective parts of reality. What about an explanation for the applicability of mathematics? Cole does not provide one, but the explanation that can be given for this feature in Cole's theory relies on the notion that mathematical entities are surrogates for other facets of reality. According to Cole, surrogate objects must have properties that reflect the properties of those facets of reality for which they serve as surrogates. So, if mathematical entities are to serve their surrogacy functions well, they must reflect the features of the physical world. This is easy to see in the case of natural numbers and basic arithmetic, because they represent quite directly how physical collections of things work. But Cole's institutional theory has a tough time explaining how more complex mathematical entities are connected to the physical world, since it is not at all clear how the kinds of logical possibilities that entities like complex numbers or large cardinals are surrogates for actually reflect the features of the physical world. In fact, the weak point of both of these explanations is that they rest on the notion of logically possible systems of objects. They are what constrains the objectivity of mathematics. And also, if there is a connection between mathematical reality and the physical world, it goes through the logical possibilities. Problem is that this notion is left troublingly unclear. Cole just assumes that there are ontologically objective facts about the relevant logical possibilities, but he does not justify this. He even brings up the possibility that it could also be entirely unconstrained what systems of objects are possible. If this is the case, the objectivity of mathematics would be severely weakened and the connection to the physical world, which accounts for applicability, would be severed. An additional problem with Cole's theory is that the question of whether mathematics is about something ontologically objective, as in Platonism, or not, is just shifted from being about mathematical entities to being about logical possibilities. And it is not properly answered. So, in conclusion, because it is not explained why logical possibilities are ontologically objective, and the explanations for objectivity and applicability rely on this, Cole's theory falls short in meeting the challenges that face social constructivism. To conclude this presentation, I'd like to return to the question I started with, that is, how social ontology can be useful for philosophy of mathematics. Specifically, social ontology gives us tools to deal with existing abstract entities without postulating any separate Platonic realms. This is what Cole's theory does by claiming that mathematical reality is institutional. But as I've argued, Cole's institutional account cannot adequately explain the objectivity and applicability of mathematics. The shortcomings of Cole's theory give reason to suspect that the Searlean framework he works with is not an optimal social ontology for mathematics. It seems that the difficulties stem from the static nature and strong focus on representations that Searlean framework has. This obscures the role that practices and actions have in the construction of mathematical reality. Cole does somewhat recognize the relevance of actions. For example, he mentions that social construction of mathematics has its origins in operations we perform. But the theoretical machinery he sets up with surrogate objects and possible systems of objects is quite heavy and static, and it does not shed enough light on how we actually get from operations to the existence of abstract mathematical entities. Rather, it raises more questions. Still, because of the merits I identified, I do think that mathematical social constructivism is a promising metaphysics for mathematics. but I suggest that the view that mathematical reality is socially constructed could be defended better if it relied on a theory of social reality that is based more on practices and less on representations. Thank you for your interest in this presentation.